Physics students, good afternoon. Mr. Fugit here. What we're going to be looking at in today's video are some problems from your assessment number 3 review, which cover over forces and Newton's law of motion. We've called that unit 4, which broadly we have titled as our unit on dynamics, or the study of why things move. Here in our problem specifically, we're going to be looking at drawing some free body diagrams and some very basic applications of Newton's second law of motion. Specifically, we're going to be looking at problems number 1 and 2 on your review. So if you want to have your review out and ready, you can do that as you're following along. As well, there are extra copies of your review and the key for those problems on Canvas as well. So I'll read problem number 1 for us, and then we will begin. So problem 1 reads as this. A book sits at rest on a flat, rough table. To get the book moving, you apply a horizontal force on the book. Draw a free body diagram of the forces acting on the book and on the table, 2 separate diagrams, as it slides across the table. Identify any Newton's third law pairs. So we have 2 objects here, a book, which I will do in black, and a table, which I will do in blue, just so we can roughly keep track of what's going on here. So we're told the book is originally at rest. It's a flat, rough table, which is helpful. And then we apply a horizontal force to get it sliding. So typically, with most objects at or on or near the earth, we start with a force of gravity. We can assume that that force of gravity is down or directed toward the earth. We are told the book is touching the table. Initially, it's at rest, so we can assume there's a normal force from the table onto the book. Remember, normal describes a type of contact force, and they're always normal forces are always drawn perpendicular to the surface of contact. We are told that we push on the book. We're not really told which direction, so it probably doesn't matter too much which direction we draw the push force. Typically, we've drawn those just horizontally to the right. And then we are told the table is rough, so there would be a force of friction opposing the push force. We would define this as kinetic friction because we're drawing the free body diagram for as the book is sliding. Now again, if you do the push force to the left and a force of kinetic friction to the right, that is also an acceptable way to draw this free body diagram. We just mainly want to see that the direction we are moving is opposite the direction of our force of friction. Okay, so now that we have our free body diagram from the book, we can look at the table. Because in order to identify any Newton's third law pairs, we have to have 2 separate free body diagrams. So for the table, we are also going to have a force of gravity from the earth pulling on the table. The table, we can assume, is probably on the ground, right? We're not told anything about a table floating in the air or on an incline, right? So we can assume the table's on the ground, which is going to mean there's a normal force from the ground onto the table. Now, that does seem to mostly take care of the forces in the y direction, except what else is touching the table here? That's going to be the book. So, just so we're not too confused with the normal forces here, I'm going to label this Fn as Fn ground, meaning that's the normal force coming from the ground. And I'm going to draw a second normal force. I'm just going to draw it out here kind of to the right. Fn. I'm going to call this Fn book, meaning it's the normal force from the book. Not the normal force on the book, but from the book. Because the book is touching the table, it's going to push down on the table. Maybe not with a significant amount of force or a huge force, but it is a force that we need to represent. To be a little bit more accurate here, we probably would have something like this. The force of gravity, and then maybe the normal force, something like this. Okay. Now, here's the tricky part. We also have this book that is rubbing against the table or kind of rubbing across the table. So, we do know that for every force, there's an equal and opposite reacting force. So, as we're pushing on the book, there's friction resisting the book as it's moving across the table. Okay? Which can be a little bit challenging. So if if the table is applying a force of friction onto the book, that means the book is also applying a force of friction onto the table. So if Fk here is to the left, that means Fk here might be to the right. So this is a force of friction from the book onto the table. Okay? So, equal, and meaning they have to be equal in magnitude, and opposite, meaning they have to be opposite in direction. Okay? So, what that would then mean, according to our free body diagram for the table, is that we have an unbalanced system of forces in the x direction. Okay? So, we have to balance that out somehow. So, as that frictional force, again, it's probably going to be very small, meaning I should maybe represent it a little bit more accurately about like this. What else is holding the table in place, right? As the book is kind of pushing off of the table as well, or pushing on the table, right? Something's holding the table in place. Now, what else is the table touching? Well, remember, the table's touching the ground. The ground is pushing the table up, but remember, there's also probably some feet on the table that are holding it to the ground. So that even as I want to maybe push on the table slightly, there's going to be a bit of static friction that's going to resist that movement. So, there's also probably a force of static friction from the ground onto the legs of the table that hold it in place. That's a bit of a kind of a reach and a way for us to make sure that we're being careful with how we represent our forces. Because if there's a force of friction between the book and the table, which there is, we need to be able to represent that. But we have to make sure, right, the table itself is not going to move. I can push the book across the table, and the table's not going to move. So I have to make sure I represent that those forces are balanced in the x direction here. Okay? So, to make sure we identify any pairs, well, we would have the force of friction between the table and the book. We would have the contact force, table pushing the book up, book pushing the table down. Notice those are the same type of force, normal force, force of kinetic friction, and same two objects, book and table, book and table. These forces of gravity, even though they're the same type of force, are not on the same two objects. They're also both in the same direction, right? F push also cannot be matched up with any of our other forces on the free body diagram for the table. So this is how we represent our free body diagram for the book and the table in this scenario. Okay? So, moving on, we'll look now at question number 2. Question number 2 reads as this. While sprinting at the beginning of a race, a runner with a mass of 60 kilograms accelerates from rest to a speed of 6.2 meters per second in 3 seconds. So we've got a runner, we'll jot down a few things here. A runner with a mass of 60 kilograms, and he begins from rest, so we've got an initial velocity here of 0 meters per second. We get up to a speed, v1, of 6.2 meters per second. We don't really know anything about acceleration yet. We know time is 3 seconds. We're not really told anything about how far the runner goes, so we might have to deal with a kinematic equation here. We're not sure. Let's continue reading and see. It says to gain speed, the runner produces a backward force on the ground, so that the ground pushes the runner forward, providing the necessary force, the force necessary for the acceleration. Calculate this average force on the runner. So in order to find the value of this average force, average or kind of net overall force, we're probably going to need to use Newton's second law. Sum of forces on an object is equal to the object's mass multiplied by its acceleration. Now we already know the mass value, it's given to us directly in the problem, however we don't know the acceleration. We do, though, know enough information about some of our kinematic variables to find the acceleration. So, delta x, if that is what we do not know, and also what we do not care about, that's going to tell us we're going to use equation 1, which reads as this. v1 is equal to v0 plus acceleration times time. v1, our final velocity was 6.2 meters per second, is equal to 0 meters per second, start from rest, plus acceleration times the time of 3 seconds. So this value is 0. So our equation can now be rewritten as 6.2 meters per second is equal to acceleration times 3 seconds. And then we can simply divide by our time to get acceleration by itself. Oh, we actually know time, so we don't have to call it just t. We can write in the value, 3 seconds. So 3 over 3 on the right-hand side, that value will reduce down to 1, and we'll take 6.2 divided by 3. That will give us an acceleration of 2.0, we can round that to 2.07 meters per second squared. So again, this first part of the problem is really just using a kinematic equation to find an acceleration. We list out our variables, we identify what we don't know and what we're not looking for. That leads us to using equation number 1, which we then can just use algebraically to find the value that we're looking for, our acceleration. So now that we're here, we can use that acceleration within the context of Newton's second law to find our average or net overall force. So the sum of forces on our runner is equal to the runner's mass, 60 kilograms, multiplied by the runner's acceleration, which we calculated to be approximately 2.7 meters per second squared. So I'll take 60 times 2.07, and I should get a value of approximately 124 newtons. So here we see a very basic application of Newton's second law. We had enough information kinematically to find an acceleration, and we used our given mass value to find the overall average or net force on our sprinter. So hopefully that gets us going in the right direction on problems number 1 and 2 on the review. Do not forget to check the key that is also located on Canvas for more help and resources. Good